Imagine if we could build a star right here on Earth, a tiny sun in a bottle that could power our cities without polluting our air or warming our planet. This is not science fiction. It is the promise of nuclear fusion, and scientists have been chasing this dream for nearly a century. So what exactly is nuclear fusion? It is the process that powers every star in the universe, including our own sun at its core. Fusion is beautifully simple. Take two light atoms, smash them together at incredible speeds, and they fuse into a heavier atom. In that process, a tiny bit of matter disappears, but matter cannot just vanish. Instead, it transforms into pure energy. Albert Einstein's famous equation, E equals mc squared, tells us exactly how this works. That little c squared represents the speed of light multiplied by itself, an enormous number. So, even a speck of converted matter releases an astounding amount of energy in the sun. This happens millions of times every single second, turning hydrogen into helium and bathing our planet in the light and warmth that makes all life possible. Now, here is where fusion differs dramatically from the nuclear power we use today. Current nuclear plants rely on fission, which splits heavy atoms like uranium apart. Fusion does the opposite. It combines light atoms like hydrogen, and this difference changes everything. Fusion produces no carbon emissions, it generates virtually no long-lived radioactive waste, and perhaps most importantly, a fusion reactor cannot melt down if something goes wrong. The reaction simply stops. There is no chain reaction to spiral out of control. The fuel for fusion is also remarkably abundant. The hydrogen isotopes needed can be extracted from seawater, meaning we have millions of years of fuel sitting right in our oceans. So let me get this straight, we have a virtually limitless energy source. It is clean, it is safe, it has been working perfectly in the sun for 4.5 billion years. Why do we not have fusion power plants lighting up our homes right now? That is the billion-dollar question, and the answer takes us deep into one of the greatest engineering challenges humanity has ever faced. Let me take you inside the actual process of nuclear fusion. It all starts with the simplest elements in existence, hydrogen atoms. But not just any hydrogen. We use two special varieties called deuterium and tritium. Think of them as hydrogen's heavier cousins, each carrying extra neutrons in their cores. Now here is where things get interesting. These nuclei naturally want nothing to do with each other. They both carry positive electrical charges, so they push apart like two magnets with the same pole facing each other. Scientists call this the Coulomb barrier, and it is a formidable wall to climb. To overcome this repulsion, we need to create conditions that exist naturally only in the hearts of stars. We are talking about temperatures exceeding 100 million degrees Celsius, that is about 10 times hotter than the core of our sun. At these insane temperatures, the atoms strip apart their electrons and become plasma, a swirling soup of charged particles. But heat alone is not enough. We also need incredible pressure, and we need to keep that plasma confined for long enough that the nuclei actually collide. When they do finally smash together with enough force, something almost magical happens. They fuse into helium and release energy. Here is the truly mind-blowing part. A tiny amount of fusion fuel, roughly the weight of a paperclip, contains the same energy as thousands of gallons of gasoline. This comes from Einstein's famous equation, E equals mc squared. When the nuclei fuse, a small amount of mass disappears. That missing mass transforms directly into enormous energy. So why is this so difficult to achieve on Earth? Stars have massive gravity to squeeze their fuel together naturally. We do not have that luxury. We have to recreate those stellar conditions from scratch. containing something hotter than the sun, in a device that cannot melt. That is the engineering challenge that has occupied scientists for nearly a century. So how do we actually achieve fusion here on Earth? Scientists have developed three main approaches, each with its own clever way of solving the same fundamental problem. The leading approach is called magnetic confinement. Fusion. Remember, fusion fuel needs to be heated to such extreme temperatures that it becomes plasma, a state of matter where electrons break free from their atoms. This plasma is hotter than the core of our sun, so no physical container could possibly hold it. Instead, scientists use incredibly powerful magnetic fields to trap and control the plasma, keeping it away from the walls of the device. The most common magnetic confinement devices are called tokamaks and stellarators. A tokamak is shaped like a giant donut, using magnetic fields to keep the plasma spinning in a continuous loop. Stellarators work similarly, but use a more complex twisted shape to achieve the same goal. Right now in France, the ITER project is building the world's largest tokamak. When complete, its central magnet will be powerful enough to lift an aircraft carrier straight out of the water. The second approach takes a completely different path. It is called inertial confinement fusion, and it uses lasers instead of magnets. At the National Ignition Facility in California, 192 massive laser beams are focused onto a tiny fuel pellet about the size of a peppercorn. The lasers strike from all angles, simultaneously compressing and heating the fuel so quickly that fusion occurs in a fraction of a second. In December 2022, this approach made history for the first time ever. Researchers at NIF achieved ignition, meaning the fusion reaction produced more energy than the lasers put in. It was a genuine breakthrough moment for the entire field. The third category includes emerging hybrid approaches that combine elements of both magnetic and inertial confinement techniques, like magnetized target fusion and field-reversed configurations are being developed by private companies looking for faster, cheaper paths to commercial fusion power. Let us talk about the number that keeps fusion scientists up at night. It is called Q, and it is deceptively simple. Q is just the ratio of energy coming out of a fusion reaction compared to the energy going in. But behind that simple definition lies one of the most challenging engineering problems humanity has ever tackled. When Q equals 1, you have reached what researchers call scientific breakeven. This means the fusion reaction is releasing exactly as much energy as you are putting in to heat that plasma. It sounds like a victory, and in many ways it is, but here is the catch: even at Q equals 1, the reaction will not sustain itself. You still need to keep pumping in energy from outside. The real magic starts happening around Q of 5. At this level, the reaction begins heating itself. The energy from fusion stays trapped in the plasma and keeps things hot. This is called ignition, and it is the holy grail for reactor designers. But for a commercial power plant that actually makes money selling electricity, we need Q between 10 and 20. Now, here is where things get tricky. There is a big difference between scientific breakeven and engineering breakeven. Scientific breakeven only counts the energy heating. The plasma engineering breakeven counts everything: the lasers, the magnets, the cooling systems, the entire facility. A reactor might have a Q of 5 from a physics standpoint, but still need more total electricity than it generates. In December 2022, the National Ignition Facility made headlines worldwide. They achieved a Q of 1.54, producing more energy from fusion than the laser energy they put in. By 2025, they pushed that to Q of 4.13. These are genuine achievements. but the lasers themselves consume far more electricity from the grid than the fusion output provides. We are talking about baby steps on a very long journey. Net energy gain matters enormously, but it is just one piece of a much larger puzzle. We also need reactors that run reliably, use affordable fuel, and operate for decades without constant repairs. The Q factor tells us we are on the right path, but the destination is still years away. So we have a working fusion reaction. Scientists have proved it can be done, but before we pop the champagne, we need to talk about what happens next, because getting fusion to work once is one thing. Building power plants that can run for decades is something else entirely. Let us start with the materials problem. Inside a fusion reactor, conditions are brutal. We are talking about temperatures hotter than the sun and intense bombardment from neutrons. These neutrons slam into the walls of the reactor with incredible force. Over time they degrade. Even the toughest materials we have, a commercial fusion plant needs to run for 30 or 40 years. Right now, we do not have materials that can survive that kind of punishment. For that long, scientists are testing specialized steels and new composites. But this remains a major unsolved challenge. Then there is the fuel problem, specifically tritium. This radioactive isotope of hydrogen is essential for most fusion designs, but tritium is incredibly rare. It costs about $30,000 per gram. That is diamond territory. The total global supply is measured in kilograms, not tons, and here is the catch: a working fusion reactor must produce its own tritium. It does this by using neutrons from the fusion reaction to interact with lithium in the reactor walls. This process, called breeding, has never been demonstrated at scale. If it does not work efficiently enough, the reactor simply cannot sustain itself. Finally, we have to talk money. Fusion reactors are enormously complex machines. They require massive magnets, precision engineering, and years of construction. All of that costs a fortune. Meanwhile, solar panels and wind turbines keep getting cheaper. Batteries are improving rapidly. For fusion to matter, it needs to compete economically, and that means driving down costs while proving these machines can run reliably for decades. Not just during experiments. We are closer than ever, but the finish line is still years away. There is an old joke in the scientific community that nuclear fusion is always 30 years away, and it has been 30 years away for about 70 years now. But here is the thing: that joke is finally getting old, and not for the reason you might think. The reality is that fusion research has been dramatically underfunded for most of its history. Scientists were making steady progress, but on a shoestring budget that changed in recent years. Private investment has poured billions into fusion. Startups and governments have gotten serious about funding large-scale projects. So when will fusion actually be ready? Let us look at the major timelines. ITER, the massive international project in France, is the closest thing fusion has to a sure bet. They are targeting first plasma in the mid-2030s, with full deuterium-tritium operations starting around 2035 or later. This will be the first experiment that produces more energy than it consumes. But ITER is not alone anymore. Private companies are moving faster. Commonwealth Fusion Systems, backed by Bill Gates, aims to have a pilot plant running in the early 2030s. T Technologies and Helion have similar aggressive targets. Now, most independent experts think commercial fusion power plants will come online in the 2040s or 2050s. That might sound far away, but consider what it means when fusion arrives. It changes everything. We are talking about an energy source that could power human civilization for millions of years. The fuel comes from seawater. there are no carbon emissions, no risk of meltdowns. Very little long-lived radioactive waste. Fusion is not just another energy option, it could be the ultimate solution for humanity.